We're going to start with this particular problem demonstrating how a line integral is evaluated by parametrization, and then we'll show a little shortcut, actually quite a nice shortcut, that we'll use from henceforth under the right circumstances. So let's look at this line integral where we have components of a vector field, say x squared y and x, and the differentials dx dy, classic line integral evaluation. And the curve C that we're integrating over is a triangular path shown here in this figure. So it starts at the origin, goes from the origin to the point 1, 0, then from 1, 0 goes up to the point 1, 2, and then from 1, 2 goes back to the origin 0, 0. Now if you recall, since each of these pieces on this line integral, in this region, this boundary of the region, since each of those pieces are straight lines, we can use our parametrization technique for straight lines by taking the initial point, or the initial vector, initial position r sub 0 vector, and then add t multiple of the difference between the terminal point, r1 vector minus the initial r sub 0 vector. And of course, when we do that, t fluctuates or goes from 0 to 1 to get you that straight line segment. So let's just take one piece at a time. And we'll start at 0, 0 and go to 1, 0. We'll call that curve sub 1. And to do that, we start with the 0, 0 vector, the initial point we're at, plus, now let's think of the difference. 1, 0 minus 0, 0 is 1, 0 vector times t. And so we come up with these components for the vector r of t, which represents the parametrization of this first piece, this horizontal piece here on the x-axis. Now if we're going to parametrize C2, which is this vertical piece, so we start at 1, 0, which is down here. We go to 1, 2. So we have the initial vector 1, 0, plus the difference, of course, is 0, 2 times t. And we come up with this expression for the parametrization of C2 in vector form, 1, 2t. Now with C3, we're going from 1, 2 to 0, 0. So we have starting at 1, 2, we subtract, we get negative 1, negative 2 times t. And so here we have the final parametrization of this segment C3 going from the point 1, 2 to the origin. Now the reason why we went through all this trouble is because we've commonly evaluated line integrals in terms of x and y by using a parameter t, so that we could just use a single variable calculus approach as t goes from, well, wherever it starts, wherever it finishes. Of course, with straight line parametrizations, we go from 0 to 1, so it's actually quite nice. But line integrals do take a lot of work, even under these circumstances. Let's remind ourselves of that. So let's evaluate the first piece on C sub 1, x squared y dx plus x dy. We recall these two components are of the vector field, and the dx and the dy are the differentials. Of course, if we parametrize x and y in terms of t, then we have x prime t dt and y prime t dt as we go on to the expressions in terms of just t. But here's an interesting thing. We recall that when we have a horizontal piece, y is not changing. So the differential dy is 0. So this whole piece drops out. And we're just left with x squared y dx, which is what we have right here. Now let's remember, with the first piece up here, C1, x was t. So we'll have t squared, y is 0. Okay, so this is going to drop out as well, but let's just go through the motions to get the hang of this. And then the differential, right? dx is actually going to be x prime t dt. So x prime dt ddt of t, which is just going to be 1 dt. All right, so we have the following structure parametrized. Of course, as we just noted, since we have this piece here, the y equaling 0 all the time, well, that's going to just give us 0. So all that work for nothing so far. What about C2, this vertical piece? Well, we kind of get a nice little shortcut here as well, because this vertical piece, another way to say it is, it goes along a piece of the line x equals 1. So if x is always equal to 1, then x is not changing, so this piece, the differential dx, is going to drop out because dx is actually equal to 0. So all we have to really concern ourselves with is x dy, which is right here. All right, let's go back now to the second parametrization of C2. So x is just 1, so we put a 1 here. dy, as we said, is y prime t, y prime of t dt. So what's the derivative of 2t? That's the expression of y in terms of t. Derivative of 2t goes right here. That's going to be 2 next to the dt. So we'll just have an integral of 2 dt from 0 to 1. Well, of course, that's just equal to 2. So finally, we've captured something other than 0 from this line integral. Now, the last piece, C3, we don't have the luxury of saying, well, one of the variables never changes, so it's going to drop out. We actually have to use both components and do some calculations. And here's where a line integral can get a little more involved, but it's not too bad. Let's see. So we have x squared y dx, x dy. Okay, let's follow the recipe here. X is 1 minus t, y is 2 minus 2t. So here we have 1 minus t squared times 2 minus 2t, derivative of 1 minus t, which is what x equals, right? d dt that, and put a dt next to it. That'll give you dx. And similarly, with regard to the dy integral, let's see now, we have integral x dy. Well, x is equal to 1 minus t again. There it is. And dy would be, well, here's y in terms of t, so dy would be d dt of 2 minus 2t times dt. Now we just got to simplify that and evaluate. Let's think for a moment now. Here we have a 2 minus 2t. If we factor out 2, we take it outside, well, there's that 2. But somehow they have now, let's see, t minus 1q. Let's see how we get that. Well, let's think now. Here we have 1 minus t. If we take out the 2, we have another 1 minus t. So that's 1 minus t cubed. 1 minus t cubed instead of t minus 1 cubed. Let's see what they do here. It must be this negative sign, right? The derivative of 1 minus t with respect to t is negative 1. And if you look at 1 minus t cubed, you could look at that as being negative 1 cubed times t minus 1 cubed. And you factor out the negative 1 cubed, it's a negative 1, and negative 1 times negative 1 is 1. So we're left with just t minus 1 cubed. And over here, taking out the 2 once again, and derivative of 1 minus t is just negative 1. Here we have another 1 minus t times negative 1 is t minus 1. So these are very familiar integrals, and if you use your integral techniques, you will get negative 3/2. So that completes the circuit, if you will. We've started at the origin and we wound up back at the origin. Notice we have this counterclockwise orientation of the boundary curves coming all together. Each of them are piecewise smooth. So now we're going to put it all together and finally evaluate this line integral that was given originally. You just add up all the pieces. So what's 0 plus 2 plus a negative 3/2? Well, that gives us a final result of 1/2. Okay, so this slide looks pretty dense. It has a lot of line integral calculations in it. It takes a little work to do line integrals even when you parameterize in terms of t. Let's see if we could take another approach. So same region, same line integral, but now, for the moment, for no apparent reason, I want you to instead evaluate the double integral over the region itself, over the region R, of this expression. Let's see. Partial g with respect to x, so g was the second function here, right? That would be the x, minus partial f with respect to y. F is this first function, that would be x squared y. Well, let's see what happens. What's partial g with respect to x? Well, g's over here. Partial x with respect to x, that looks like a 1. And minus partial f with respect to y. Here's f with respect to y. So we treat this like a constant. It looks like x squared. Okay, so we have 1 minus x squared, and we know the dA differential, the area in terms of x and y. You could do dy first, then dx. Let's take a look at the picture. Now, if we are integrating with respect to y first, partially with respect to y, that means x is being held constant. So if we held x fixed somewhere, then y would vary from 0, as low as 0, all the way to as big as, well, it varies as we go along this piece. Well, what's this? What's the name of this piece in terms of x? Well, this is, if we start at 0, 0, and you wind up at 1, 2, this is a little piece of y equals 2x. So the upper boundary of the inner integral of this double integral will be 2x. And so if we integrate that, let's think. Integral this thing, well, this is just like a constant if you're integrating with respect to y. So you'll have 1 minus x squared times y, and y is going to go from 0 to 2x. So that's just going to introduce another factor of 2x times 1 minus x squared. And 2x times 1 minus x squared is simply 2x minus 2x cubed. We evaluate that now from 0 to 1. And we realize it's from 0 to 1 because x goes from 0 all the way to a maximum value of 1 in the region. And we have, oh my goodness, the same answer we had before of 1/2. And of course, the question is, well, does this happen all the time? And the answer is yes, under the right circumstances. There is, in fact, a connection between certain line integrals around a closed curve and double integrals over the region enclosed by the curve. And that connection is called Green's theorem. It's of fundamental importance in the analysis of fluid flows and in the theories of electricity and magnetism. And Green's theorem goes something like this. Let R be a simply connected plane region whose boundary is a simple closed piecewise smooth curve C oriented counterclockwise. That's very important. Oriented counterclockwise. You'll see in a classic proof of Green's theorem the reason why this is true is because of how the differentials dx and dy interact as you go along counterclockwise. And if you do so, you'll come up with this formula that we're getting to. If f of xy and g of xy are continuous and have continuous first partial derivatives on some open set containing R, which is a long mouthful of interesting preconditions, but if you meet all those preconditions, then you can finally say that the evaluation of the line integral is simply the same thing as a double integral over the region that that boundary encloses. So it's common practice to communicate the counterclockwise orientation, the fact that you're dealing with a line integral. It's a common practice to denote a line integral around a simple closed curve by an integral sign with a superimposed circle in the middle of the integral sign itself. And sometimes a direction arrow is added to that superimposed circle to indicate if the integration is clockwise or, of course, as you see here, counterclockwise. So you'll often see Green's theorem expressed this way as well. So look out for that neat trick. You can avoid a lot of work with regard to line integrals if you realize you have the criteria that you need to apply Green's theorem. So we hope you enjoy that video.